Hello everyone, it's January the 9th. Alright, I'm changing the time I'm doing this. I'm doing this in the morning. There are many reasons behind this, but I feel like it's always good to start the day, do this the first thing in the day, and help me wake up. Alright, so I'm gonna get this and what's the other thing? This is the thing. We just implement this and then we have to do that one more time, basically. Alright. Leaf similar trees. Consider all the leaves of a banana tree. From left to right order. The values of those leaves form a leaf value sequence. For example, in the given tree above, the leaf values. Okay. Two banana trees are considered leaf similar if their leaf value sequence is the same. Return true if and only if the two given trees with the nodes, two roots are leaf similar. Okay, so we basically need to traverse the leaves, right? We traverse the first leaf and we traverse the second leaf and see if the two are the same. Now, how do we get the leaf? The question is, how do we get the leaf in the order that it is? Is it the in order, the left? Is it the left, right root? Does that work? I guess it doesn't really matter, right? Because whenever we find if it's the leaf, so left of the left, so okay, it's the leaf. Then I can do left root, right, left root, right. Yeah, I think that will work. Left root, right will work. So yeah, we go left or right, we traverse it, and we put them into an array list. Is there like a better way to compare if the two array lists are the same? Array list. Oh, isn't it equals? Contains. Oh my god. Why is it so complicated just to try to compare the two? Let's say it can have equals. But nobody's talking about it. Granted, these are all many, many years ago. Oh, I think this one was... Okay, this one just says. Oh, he doesn't care about the order. Okay, that's why it's complicated. Yeah, I just do equals. Perfectly fine. Okay, let's get on to it. I'm gonna go to 12. So what we need is list integer. Right, we call this leaves one. Right, and then list integer leaves two. Okay, and a private void traverse node. Okay, so we say if node is not equal to null, right? Then we will do first is traverse node.left. Oh, but how do you know? Well, here, if node.left is equal to null and node.right is equal to null, right? That means you are a... Holy, how do I know? Oh, you know what? These are not right. So these are not right. So I have to put them here. Array list. Oh, say list integer leaves. This is leaves.add node.val. This is the leaf, and then traverse node.right. Leaves. Okay, and then I will go traverse root 1, leaves 1, traverse root 2, leaves 2, and then we return leaves 1 dot equals leaves 2. Okay. Is this good enough? I think it's pretty much good enough. Yep. traverse 2 trees to obtain their leaves. Eight 72. Oh yeah, it doesn't really matter actually. Yeah. Okay. Go up. All right. This is done. All right. We want to implement this. All right. So again, we're gonna do this one more time. Okay. Let's do this one more time. So what we have is nums1, nums2, right? So we want is sort x decreasing, right? And then sort, so we sort x decreasing, and then we'll sort queries x also decreasing. And then for all x's that's larger or equal to qx, that's queries x, we will create, right, we'll create a monotonic decreasing array on y's and monotonic increasing on x plus y. Actually, no. I think I got it wrong. It's a monotonic increasing on y and then decreasing. Because increasing on y, you can do binary search. I can find the first one, right? And then decreasing on x plus y. It's decreasing on x plus y. So the first one you find is correlated with the largest x plus y. Now, why will this work? Because all the larger than x is already done. So you're gonna find whatever is on here, right? You're gonna find whatever is on here. And then because it's gonna be monotonic increasing, so any y that's small we can ignore. Because if a y is small, then its x plus y is going to be small. It's just useless. And then we're looking for bigger, like when y is going to be bigger. So if you have a smaller y coming up, then this will be small. And you can always find a better option, so you ignore. So you get a big one. And for the big one, you need to go x plus y monotonic, which means if it's big, you have to record it, because a big y can be beneficial. Okay, so that is how we're gonna do it. Now the question is, do you want to do this in Java or Python? Oh, I think it's no brainer. It's gonna be Python. 2736.py. 1 1000, 2 1000, 3 1000, 4 1000, 5, 6, 7, 8, 9, 10. Wow. Talking about being slow. It's ridiculously slow. I don't know. I mean, it would take just like so long to get it to open. Alright, so what we're gonna do is we're gonna go to the end. Right. And just gonna write it again. So we'll call it solution 3. You know what? I need to put enough How do I create more empty lines? Oh, this. All right, and then there we go. Now we have no idea where it is. And this lead. Thank you. That's awesome. Here smells wonderful. All right, let's implement this. So first of all, we need to sort. So we're gonna call something called xy. It has to be sorted. I think I can go zip nums1 and nums2. All right, so that's xy. We'll sort it. Oh, hold a second. I think reverse need to equal to true. Alright, so reverse is true. We're gonna sort that. And then we're gonna sort the queries. Okay, so qxy sorted as well. But this one's a little bit different because it'd be qx, qy, I. Okay, for I, qx, qy in enumerate queries. Oh, shoot. Right, and oh, I probably have to add this. Right, then go to the end, reverse equal to true as well. Okay, so now we have the queries and this. And we need to go through the query one by one, and then we need a rest. That's just gonna be this times len queries. Okay. Now we're gonna go through qxy, right, for each of them. So for qx, qy, I in qxy. Now what we need is to first, we need a stack. Right, and then we also need an index. Right. So what we're gonna do is find every xy whose x is larger than qx. Right, whose x is larger than qx. And what if we don't have any x that's bigger? Oh, that's fine. If we don't have, we just skip. Right? If we don't have, we just skip. Yeah? Because that just means your query is too big. Right? Your query is too big. Yes. Your query is too big. And of course, we're going to search inside the query. And if you don't have anything in, yeah, because you start, we're gonna say if we have anything bigger. Okay, so we should say if while index is smaller than len xy, okay, and xy index, alright, xy index 0 is larger or equal to qx. Alright, then we say blah blah blah, and at the end index need to plus equal 1. Right. Okay, what is this? Now what we need to check is, let's say, check the y, check the y, because I'm popping basically. I take away this x and y, and this y has to be larger than what we have. So if stack, all right, and so stack, we're gonna put stack I shall equal to y and x plus y, and y is increasing, y is non-decreasing, whereas x plus y is non-increasing. So if we have a stack and stack minus 1, 0, right, minus 1, 0, stack minus 1, 0 is y. If this y is smaller or equal to y, xy, index 1, right? If that is true, that means we can put this into the stack while stack and stack minus 1, 1, right? So we have it decreasing if this is smaller or equal to, yeah, we can do smaller equal to, we can pop xy index 0 plus xy index 1, then stack dot pop, right? So blah 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 blah, we pop everything, and then at the end I'm gonna say stack dot append xy index 1 and xy index 0 plus xy index 1. Okay, and then we go back again. Ooh, qx, right? If it's larger than qx, now we keep going until we don't find any more. Okay. Now, what's this? This is when we finish preparing the stack. So now the stack is done. Okay. Now the stack is done. What we're gonna do is get a qy, so we can binary search the qy. Right. I'm gonna say j bisect left stack qy key lambda tuple, we use tuple 0, right? J is we're gonna bisect left the stack using qy because y is increasing, so wherever you find is the index of larger equal to, then we say if j is smaller than len stack, which means we find it, then res I shall equal to stack j1. This is the largest. Else res j, no, I is equal to minus 1. So this basically says couldn't find, right? Cannot find a y. Larger than qy. So far. Qy while x is larger than qx. Yeah, that's the case. So with that, We can return res. Okay. Yank it. Oh, let's take a look. Is one correct? Name solution, oh, of course. All right, it's not right. Okay. It's alright. It's alright. This should be right. This is alright. Rest is right. Stack. Okay. Index smaller than len. It's just to make sure that we can keep going. XY index. This is fine. If stack and yeah, because I want y to be increasing, not decreasing. Interesting. Okay, so we can do some tests, suppose. And we'll do. Oh, no. Alright, now we go down. 22737. Okay. Let's figure this out. Let's print stack. Let's take a look. Oh, it is slow. The slow process is not as fast as using the other one. Empty. It's an empty array. What? What did I do wrong? Oh, I never entered this, did I? No, I did. All I need is... No, I did. Right, this is 4. And this is also 4. So the first one shall enter. Huh. But the Y I want... here. So it's not stack. Stack is empty. Maybe the append shouldn't be here. Maybe just say if not stack. Yeah, maybe here. Maybe we should say if not stack. So stack is empty, then we don't have any of this. Then we'll append if stack is empty. If stack is not empty, all right, then we do this. Stack is not empty. Then we need to check this. Okay. Nope. Oh. We have an error. All right. Oh, we pass. I might as well. Okay, okay, GC 3J. Nope. Undo 2J. 2J. Okay. All right. This one looks right. Oh. Oh, it's yank. All right. Ah, come on. I made this mistake all the time. All right. This one looks right. There we go. Huh. That's exactly the same method. So it's if not stack. And all right, now let's check our solution previously. Now we can delete from 24 all the way down. So we can say D21J. There we go. All right, let's compare. Compare the two methods. While. Oh, that's fine. This is the one. If not stack, and that's the thing. That's the thing. Alright, other than that is the same, right? This is the thing. If not stack, because if stack is empty, we want to append something, right? If stack is empty, we need to append something. If stacks are not empty, we need to check. Yeah, that's why the earlier version is wrong. All right, so nothing more. All we want to say is here. This is basically another practice, right? So yeah, another practice session, another practice on this problem. I was not able to do it again from scratch. So this problem needs to remain in the list for a future review. Yeah, that's basically how it is. Very unfortunate. I thought I was able to do it, but move this down the queue. Okay. All right, we got some time. Let's have some fun. Let's get a new one going. Minimum index of a valid split. An element x of an integer array of length m is dominant if its frequency times 2 is larger than m, where frequency is the number of occurrences of x in an array. Note that this definition implies that array can have at most one dominant What the hell is M? Can have at most one dominant element. Have at most one. Why? Oh, what the hell is M? M is a length. Dude, M is a length. Okay, so if it's a dominant, if 2 times is larger than 1, that's correct. At most 1. Okay, you're given a 0 indexed integer array of length. Why? Why? You have M and then you have N. Just use the same. With 1 dominant element, you can split nums at an index I into 2 arrays. But the split is only valid if, for sure, I has to be valid, and the split have the same dominant element. Here denotes the subarray. Both ends inclusive, particularly if j is smaller than I, then denotes an empty array. Yeah, but oh, you can be an empty array, right? Return the minimum index of a valid split. 0, 1, 2, yeah. 0, 1, 2, 3, 4. Damn. It has to be larger then, right? Which means if we have an even number and then the frequency is the same, that is a bad. That's not going to work. Therefore, you cannot do 2, 1, 3, 1. This is bad, right? Because 2 times 2 is equal to, so this doesn't work. So you have to extend a little bit more. In this case, it's not possible because there's no valid split. Wait. This one doesn't work? Holy crap. 1 times 2. Oh. A single one doesn't work. A 2. Oh, no. This one works. A single one works. And here is a single one, right? Oh, yeah. Single one works because it's 1 times 2. Yeah. What doesn't work is this, because this is 3 and this is 6. Okay. So, should we look for the dominant? Yeah, we can go through. And we can get a dominant one. That's perfect, fine. And then what? Well, it's asking for... Okay, so this, like, what's the minimum kind of problem? Usually we can try using binary search for this. Yeah, we'll probably have to go through the whole thing. We probably have to go through the whole thing just to find the dominant one, right? We need to find the dominant one, and then, yeah, so we get a dominant one, and we can do a binary search. I say index from, 0, low is 0, high is n, so we get to the middle, and then that could be, let's say, the start of the second one. It doesn't matter, start of the second one. No, end of the first one, right? Then what we need to see is if we can go through the whole thing to find if it's, oh yeah, it's possible. It's more than possible, right? O1 log n can definitely solve this. We can do this because at each split we just use the same. We just go through the whole thing, we find its counter. And then we go through the same thing and we find its counter. We can even write a function for that. and see if they are the same. Yeah, we just need to see if they're the same. Okay. But if we go through the whole thing, we have a counter, then we need to find the max of this counter. Oof. Yeah, it's fine, I guess. Well, it's fine, and I have to have only one. I had only one. Yeah, we can do that. So that's fine. O(n log n) is fine. We can definitely write something for O(n log n. But maybe, just maybe. So if we go through the whole thing, we can count. Right? In this case, 1, 2, 3, 4, 5, 6. Right? We have 6. The dominant one has occurrences of 6. Right? It has occurrence of 6. So if I go through the front, and as we go through, we count the number of ones. How many? Right? So like here, 1 is not dominant. This is not dominant. This is not dominant. This is not dominant. And this is the first time it becomes dominant. Then we check the remaining. Oh yeah, I think this is a better solution. Right? This is the first time that 1 is dominant, and I know the length. I know the count. I just check if it's dominant. If it's dominant, then we're done. Yeah, we can solve this in O(n). This is okay. Not really that hard. All right, so first things first, we need to go through the things, right? So we can, let's say n equal to num_length. I think it's the size. All right, and we go through the whole thing, and then we keep count, right? So we say for. We need to keep the count. Okay, map. Integer, we call it counter, equal to new hash map for int n of nums. Say counter.put n. Counter.get or default n 0 plus 1. We say if counter.get n times 2 larger than n. Int dom is, I would just do it dom. Okay, then for this one we'll say dom is equal to n, and it'll break. Okay, so now I have the dom. Then for int I 0i smaller than n I plus plus, right? And then we'll do the same thing. We need to count. So int count dom. If nums_i is equal to dom, then we say count dom plus plus. All right, it's telling me that it's not defined, so I define it to 0. Okay, so dom plus plus. Wait, what's wrong with here? Oh, good call. Stuck it. All right. We say if count dom times 2 is larger than I plus 1. This is the current length of the left, and the remaining is, oh shoot, Cannot break. I need a count. I need a counter. Damn. Right, if it's larger than, I just do DOM, but I do need a counter. Ugh. So counter dot get DOM. This is a dominant minus count DOM. This is the remaining, right? So the remaining frequency times 2 needs to be larger than the remaining length. Is n minus I. That is the remaining length. So 0 and the remaining 0 length is 3 minus 1, right? Minus 1. That's the remaining number. 0 1 is 3 minus 1 minus 1. Yeah, so that is, if this is good, then we should just return I. That's the first time, right? If not, blah blah blah, we in the end return minus 1. All right, so, oh no, yank it. Oh no, this is yeah, this is fine. We don't have a yank yet. All right, let's try this. Man, I have confidence on this one. First find the dominant number and its frequency. Then go from left to right and keep the count of the dominant. For each encounter of the dominant, see if it is still dominant on the current left subarray, and then check if it is also dominant on the right subarray. We can do this check, right? Do this check because we know the total count of the dominant and its count on the left. We return the first index that satisfies both. We don't even need to do any search, right? Just on it. All right, let's run this. Booyah! That was correct. .java. All right, that'll be it. Yeah. 9. All right, that'll be it. I need to start working. All right, I will see you guys tomorrow. Hold a second. One more thing. Just check. Boyer Moore algo. Actually, I want to read this one. Maybe next time. I need to read this one. I remember this. I think it's ON, like one pass to find. Anyway, I'll do this later. I'll see you guys tomorrow. Adios.